Hi, hi everyone. Welcome to our fourth edition of the almost quarterly Rust meetup from the Rust meetup group in Munich. Today we're going to talk about fuzzing techniques, and well, in extension to that, about tracing and how to do that causality based rather than correlation based. We're going to start with Harui Katora. The author or the maintainer of the image crate, which is going to tell us well, not something, but a lot about fuzzing techniques today. Take it away.
Hi guys. So the idea of my talk is to present some high-level overview of fuzzing because it's actually not that complicated, and maybe to take away a bit of fear and to show some ideas on what you can customize with fuzzing and how you can automatically improve your test suite. Basically, how you can actually let your computer work most of the time. And obviously, that's very useful for open source projects like Image that are pretty big. Like I think we're at 6,000 or 7,000 downloads per day right now. And obviously, we want to avoid regressions as much as possible, although that's not always possible. I think we have one with TIFF recently, but that's because the test suite isn't as great there yet. But fuzzing helped us a lot with PNG and and the image in general. So let's get into it. What is fuzzing? So fuzzing, as Wikipedia defines it, is an automated software testing technique. And the one property that it has compared to unit tests is that it provides automatic, invalid, unexpected, or random data as input. And that's something you would have to put a lot of work into if you would do it by hand. So how can you fuzz with Rust? So there are fortunately a few libraries that you can use. So the big three are AFL, HongFuzz, and libfuzzer. These are all not native Rust libraries, but C libraries. So they're just bindings to the C libraries. But what you can do is basically you define a 3-line harness for your fuzzer, and the fuzzer provides random data as input, which is a byte slice that you can interpret however you want. And then you run that, run your target on the byte slice. So you execute your program on that byte slice as input, and you test if it crashes. So usually you accept that an error happens because obviously programs can error, and erroring is useful if you do it in a very controlled manner. And Rust's error or result type is a very controlled manner. So you just ignore the result of your operation and only want to know if your program actually crashes. But of course, if you want to find out that something always succeeds on any input at all, then you could unwrap the result, and that would basically reduce it to a crash if it errors. So these 3 libraries all give you a library component, so you can write basically a main function, and then you can execute those, and they all come with different types of harnesses to execute programs. So different ways in which you can schedule basically the fuzzer to work on your data in your program. But there are 2 integrated tools that make this a lot easier, and you can just install them with Cargo. So you install a Cargo Fuzz or AFL, and those will offer you a lot of usability around the fuzzing tools. So I want to go into one of those in detail, and that is the Cargo Fuzz program. So a very, very brief guide. So what can you do with Cargo Fuzz? So it works similar to the main cargo tool. You can initialize a new fuzzing skeleton, so that sets up a directory, and then you can edit some binaries, basically Rust files, where you write exactly those, well, not 3 lines, but probably more, but those fuzzing harnesses you saw earlier, and then you can execute one of those harnesses and see if the fuzzer finds some bugs, some crashes in your program. And if the fuzzer finds a crash, then it will put the input of that crash into a directory, and there it will just be a file, and you can check that file. You can see if you can spot anything that's odd about it manually, or you can run it again on that input, and you're probably guaranteed that it will crash, except if you have some global state that you don't reset well, which is another good reason not to have a lot of global state. But the last thing is there might be a lot of files, so you can minimize the test cases, and I'll get into what minimizing even means here in just a bit. So that sounds like magic, right? You initialize some fuzzer, you write a very, very brief program, and then you get test cases for free, and probably a lot, and very fast for very most programs. Actually, typically you have some logic errors that are, let's say, easy to find if you search literally thousands or millions of inputs per second. And obviously you can't search millions of inputs per hand, but of course your CPU is powerful and it can do that. So it generates random input that can be efficient, right? Because if you think, let's say, JSON or XML, then most of the input is totally invalid, right? If you throw a random byte sequence into an XML parser, then mostly it will just say there's an error. Here's a byte that's unexpected. Here's a tag there that's not closed, etc. But actually, there are a few tricks that we can use to make this a little more efficient. So one of the cool things is we can take a look at coverage. So the paths that a program can take, the different paths. And we can say that if we have a lot of path coverage, then we have a lot of testing, right? That's also the idea behind unit tests, to get 100% path coverage. And so the idea is, if we can increase the path coverage by automatically finding new inputs that generate new paths, then that's obviously going to improve our test suite. So what we're doing is we don't choose exactly randomly, so not uniformly randomly, but we choose weighted inputs. And then we just change them a little bit, and then we look if there's a new execution path. For example, in PNG, we had around 800 to 1,300 really different execution paths, which is a lot, but also not too much, right? You can imagine that we could find them and enumerate them, actually. And then we can, when we observe the actual execution of a program, then we can, by tracing, find out if we've hit a new execution path. And if some input executed a new path, then it obviously must have been better than the inputs before. So we increase the weight of that input so that we generate more of those inputs. And that can actually get a decent efficiency. It won't be great. Like for 100% path coverage, you will still have to wait literal CPU months, even on compressors, but it gets you a lot of coverage quickly. So a lot more than uniformly random. So now that I hope a little bit of the magic is gone, there's one cool thing which Cairo Fuzz can do extremely quickly for you, is you can fuzz for different pointer widths. Because on the Linux target, there is an i686 target that lets you run programs on 32 bits. So that's maybe one cool thing which a lot of libraries might not be prepared for. So we found a couple of bugs because Rust as a new language enjoys the freedom that most computers nowadays are 64 bits. And you can cast integers from usize to u64 with no problem, and the other way around. And that's risky. So you might have some overflow issues that you're not aware about if you only test on 64 bits. And so it's cool that this just works natively on any Linux system. Just a random tip here. So if you want to build your own fuzzer, because now I've explained how it's done, right? Not really. That would far exceed the talk, but you can have a look at a video series by Gamozo Labs. I've placed a link here to the blog post. And that's writing a fuzzer from the ground up to fuzz like really generic binaries. And one cool thing is it writes an emulator, because in an emulator you can obviously observe every effect without tracing, and you can be perfect about your observation. So you might want to have a look at that. Okay, so now let's get into more interesting fuzzing. We've covered the basic, it crashes. But what if you don't want to check if your program crashes, but you want to have some unit test-like observations? You have an idea of how your program should behave, and you want to check if that idea is correct, if that property actually holds. So for example, in JSON, one idea might be that all digit sequences with more than 0 digits are valid numbers and therefore valid JSON. Is that correct? So there are also tools to test that as unit tests. So the two libraries are QuickCheck and PropTest. They work similar, although PropTest is a little bit more advanced because it allows you to specify the input here as a regex. So you can just place a regex and say, for all input strings that conform to that regex, I would expect that the JSON parsing succeeds and it doesn't error. It's an okay result. And then you can check if it's actually a number, but I've omitted it here for brevity. So seems simple, right? So let's run it. And then if we run it, we see, ooh, it panics. So that unit tests, you just run cargo test. That unit test panics. Why does it panic? It also tells you. It says the parsing errored with invalid number at line 1, column 2, and the input, which is the actually interesting part, was 0, 0. So it turns out the JSON specification says that you cannot have a leading 0. There is some reason about octals. So octal numbers in JavaScript would be parsed differently, so you cannot have that in JSON. Okay, so we've learned, and now we can check a different property. So what if we check instead that all numbers with the same pattern before, but they mustn't start with 0? So obviously we could write a fancy regex for that, right? We could adjust our regular expressions to match the pattern and the pattern that we don't start with 0. But I wanted to show like how you can combine these different techniques. Here, if the number starts with a 0, then we just don't do anything. And then obviously we can't crash. And since the fuzzer tries to find a crash, it should avoid numbers that start with a 0 quickly, which is maybe also the biggest weakness of fuzzers. So while they can observe paths, they are obviously not perfect. Let's say if your last few instructions in your program have a new path, then it can't completely trace back how it gets to execute that other path. So it must guess. So if like one of the conditions here was that the number is not nan, then finding that one path through the program that actually leads to a nan output might be hard, and it wouldn't find that quickly. But that's not really the biggest problem, right? We still write our own unit tests. We still write the normal unit tests, still some human knowledge. The one thing is this runs in less than a second. And in less than a second, it found the error in our assumption, and we could fix it quickly. And then this passes. Okay. So next cool idea is model checking, right? We had some fixed input, but then we did exactly one operation on that input. But what if we want to model a data structure? For example, a stack. So what can a stack do? We can push and we can pop. Right here, I've substituted the item you want to push with the unit struct. Because it's not important, it won't be important which value we push. But now we might ask ourselves, is a vec an accurate simulation of a stack? Well, might be trivial, but it's still cool to check. So how can we use fuzzing for this task? So the one idea that you might have, well, programs are sequences of numbers, right? So what if we just interpret our input as a program, and then we run that program, and then we assert something about the property of the stack after the program has been run? And that's the idea of model checking. So here in our input, we get one large program, which is and a bunch of operations that we execute one after another. And then we run that program, which means we execute each instruction one at a time. And here, the property that we want to check is that the length of the stack afterwards is the length we expect, which might not be the case, right? A vector reallocates internally. There could be an error in the relocation, etc., etc. Who knows? And so with each instruction that we execute, so here pushing is instruction, we expect that the length increases by 1. And when we pop something, ignoring a failure to pop nothing because our stack is already empty, then our length decreases by 1, except if it's already empty, of course. And then afterwards, we can check that the stack length is the length we expect. And here, libfuzzer gives us our hardness, so this becomes just a normal test. And if we run that test, then it tells us it can't find any input where this test fails. And we can conclude that it's at least likely that the vector simulates stack. So obviously it's unit testing, so we can't get any definitive answer. But it gets us a lot of, it gets us a lot of coverage. For example, I think it's a very similar technique found a bug in ShortVec, in one of the ShortVec implementations. where popping after the vector was heap allocated screwed the capacity in some way, but I can't remember the details. But yeah, a short vec is obviously a different sort of vec, so it might have other bugs, and it should still behave like a stack. So if you write this harness once, then you can insert any kind of vector implementations that you have internally, and you can check them if they conform to the model of a stack in that case. Of course, you could design a very, very sophisticated model of a vector. For example, assert that the ordering of elements doesn't change while you push and pop new ones, etc. And then you can even check fancy data structures such as slot maps or hash maps. Yeah. So we've already seen that it's a tool to write programs. So can we actually use fuzzers as a tool to rewrite programs? So imagine you have written a parser for this regular expression, an A followed by a number of BAs and then a B. And someone else tells you, hey, this is equivalent to AB, a positive amount. And you don't really trust them. Or you don't trust the implementation. Or you've written the new implementation and you don't really trust yourself. And of course, in reality, those specifications might be a lot more complex. So for example, in a compression standard, you have written a new decompressor or some kind of archive format. And can you use a fuzzer to help you write those kinds of programs? And yes, you can. So the idea here is you execute both the old and the new version of the program, and you check if they yield the same result. And you check if they have the same result by simply asserting that they have it. And if it panics, then either the old reference implementation has a bug that crashes, or your implementation has a bug that crashes, or the results are different. And either of those three cases is good to check. So this gets you basically a lot of useful data. So yeah, you do just that, and with 3 lines of code, basically, you have a useful tool that gives you maybe also a reference implementation. So if you have a very slow implementation of some standard, but that's easy to see that it's correct, and you have a new implementation that's fast, but it's incredibly hard to check, then you can use this kind of fuzzing to check if those 2 versions give the same output, if one is actually an optimized version of the other. So this helped us rewrite the LZW decoder, which has some subtle bugs for different widths of different word widths. So you can be off by a bit, and then your whole output gets corrupted. And those are subtle to miss. They occur after 2,000 bytes, so good luck checking them manually. But the one cool thing is, of course, you can, after you've verified that your implementation is basically okay, you can replace the reference implementation with your own implementation and rewrite another incremental improvement on top. So you can verify that incrementally better programs and faster programs still give the same or very, very close to the same results. So, of course, you don't need to check that the old and the new result are completely the same. You might want to check that the new version is more generic than the old version. So it succeeds in some inputs where the old implementation fails. And of course, that's also easy to write as a fuzzing target. So You just check the old implementation, and if the old implementation succeeds, then your new one must also succeed and give the same result. But if the old implementation failed, then it doesn't matter what our implementation does, but it shouldn't panic. It shouldn't crash. So we execute it and just ignore the result. Similarly, of course, you don't need to check for equality here. You could ignore an inequality on error if you've improved the error type, for example, or you've redesigned the error type. You can check that the output is the same except for some details that you know the old implementation has missed, or that you want to ignore because it doesn't semantically matter. For example, some high-level bits that everyone must ignore either way. So you have a lot of freedom in how you design, or how you use this structure for your own fuzzing. So now to the last idea on how to use fuzzers, which might be the one idea that I haven't seen anywhere else, at least not not in that manner, and that is to generate regression tests, which is important for image for an interesting reason. So say you have found a bug, but you have no usable regression test. So for example, the regression test is incredibly large and you can't check it into your repository. Or in the case of image, the regression test is an image of which you don't know the copyright status. So you can't redistribute it, so you can't check it into regression tests. So what do? You're faced with the knowledge of the bug, but to actually have a regression test that tests that specific bug might not be simple. Because, well, for a multitude of reasons. For once, you might not actually have the whole path of execution until the failure. Because maybe you've just spotted the failure in code, because Rust makes a lot of failures obvious. And the backtrace has told you there's a bug there, and then you fix the bug, but now you don't have any idea how you even got there. Or it might just be very complicated. For example, you must first compress some part of the data. So there are two main ideas that you can apply. So first is to use the existing test and run test case minimization. And what that does is it's based on the coverage idea. So the fuzzer will modify the input while trying to maintain the same path through the code. And that works surprisingly well sometimes. So for example, in a lot of images, there is framing data. So there's one number that tells you how much bytes of pixel data or other data follow. And so the fuzzer can find out that decreasing this number doesn't actually change a lot, right? And then it can just drop all the payload of the image. It's not perfect, of course. Some changes might be very complicated, and usually the fuzzers only apply 2 or 3 byte modifications at a time. And if there's no path from one input to the next in that simple manner, then of course, the idea doesn't work. But it at least got us down from 30 megabytes or so to a few kilobytes in one JPEG image. So basically, I think it dropped most of the image data and only left some header structure alive. And that was then workable, because then in 30 kilobytes, you can actually inspect the thing with a hex editor and apply human knowledge to change a couple of bytes by hand, or actually move some sections around if they're short enough. And then there's also a very, very different idea, and that is we just synthesize a totally new regression test, because obviously the minimized test might still have some amount of information from the non-usable test case, which of course for IP that's a problem. So what if we just create a completely new regression test that only was created from the void and the knowledge about the bug? So for this, we can also use a fuzzer. So what we do now, we don't care about crashes. We just care that the old parser crashed and the new parser doesn't. And then we panic. And this looks totally weird, this structure. But it's actually very simple. This program crashes in one path, or yeah, in most cases, except some very bad corruption. So this crashes in one path if we go through the whole program, and then we hit the panic at the bottom. That's the only real source of a panic crash here. And that crash happens if the old parser did not succeed and the new parser did succeed. So that's exactly what a regression test would look like. It doesn't succeed in the old parser, it succeeds in the new parser. Hence, that's a regression test. And then we can just throw this into our favorite fuzzing tool, make a fuzzing harness out of it, search for it, and then hopefully after some time it gives us a usable regression test. And we shouldn't use one of the unusable regression tests as a sample, but of course we can use our whole database of other inputs that we might modify to get to this regression test. And if we knew that there was some specific error that we want to avoid, then of course we can substitute the catch unwind here by a test against that error, etc. And you can modify it in many, many different ways. Okay, so what should you remember from this talk? So three things. So first, fuzzing is a technique, not a single tool. It's the idea of using random data that's very cheap and that gets you the coverage over that your unit tests would normally get for you, but automatically. Because energy is, at the end of the day, cheap enough. And you have computers, and the perfect utilization is 100%. Less than 100% means you don't use it efficiently. And yeah, the last thing is the fuzzing, of course, it scales, since it randomly generates inputs, it scales with cores pretty much perfectly. So just go for large core counts for a few €100. Yeah, and it gets you a lot of coverage and very quickly. And the experience with C programs shows you have missed bugs and you have missed crashes, even if they are not memory unsafe. So just do it. So thanks for listening.
Thank you very much. That was a really good talk. Did you also use HongFuzz in the past, or did you just stick with libfuzzer? CargoFuzz.
Shortly, I used HongFuzz shortly, but I found, well, at least in my experience that I had with it, it was harder to compile because CargoFuzz, the tool is incredibly easy to compile. I've never had a single linker failure or anything in the last year with it. While HongFuzz, I always had a few couple of bugs in nightly versions, and you have to adjust some settings manually to get it actually to a fast state, I think. And CargoFuzz does a lot of cool magic behind the scenes to get you only those compiler flags that you really need for a fast fuzzing. And then the other impression that I had, one cool thing about AFL is that it gives you a nice UI of progress. And Hongfuzz, I didn't get it to have such a nice user experience. So it didn't have the user experience of AFL and the let's say efficiency of CargoFuzz, libfuzzer in a simple setup. And I just couldn't invest the time to play around too much with the settings.
Yeah, so. Makes total sense. Just asking because my biggest experience is with Hongfuzz, and I just wanted to know if, well, regarding effectiveness, if there's a difference, because I've seen statistics that like it really depends on the actual input distribution that causes the issues and the type of input. It like some fuzzers perform better than others, but there's no clear winner, like no clear all-over winner that takes it all.
Yeah, there's some cool ideas that AFL has, I mean, the other tools, of course, might implement them as well. So, for example, you might choose a dictionary for the initial input, like you set some structure, but then do random mutation. And I think the CargoFuzz tool at some point wanted to make the backend configurable, so that it's not only libfuzzer, but also Hongfuzz. But I don't know if that if there was enough.
There's something in the back of my mind that I think CargoFuzz supports all three of them, but I'm not 100% sure either.
No, I don't think it does currently, because it would lose a lot of to gain the generality, it would lose a lot of the a lot of the details that it currently applies to libfuzzer. That wouldn't be possible generically, and so there's some problem with the integration of the other three tools, if I remember that correctly.
You are correct. It's only using libfuzzer.
But on that topic, you can always ask the Rust community member Schnetzel.
Okay.
Because, well, he's the guy to ask for fuzzing and smoke testing, and just in general has a lot of overview over the secure working group that's also associated with the fuzzers. Yeah.
Cool. Do you know about the inner workings of libfuzzer? About like for the Hongfuzz, it's a bit of a evolutionary algorithm where they use the program counter to figure out which path is the one that got the furthest in the program. Do you know how libfuzzer does that by chance?
No, I don't.
Okay. All right, then let's see if somebody else has some questions. Well, I guess you covered it all, or we covered it all. So, yeah, thank you very much. And yeah, hopefully see you back soon with another talk here.
Yeah, would be great. And I'm looking forward to your talk. Or is that your talk?
All right. So our second talk tonight is causality-based profiling. But before we dig into the causality-based part, let's cover profiling just a little bit to have some common ground what we're talking about. Why would you want to profile something? There can be various reasons, like these are really kind of reasons that you encounter by people with some technical knowledge. There's some limitation or something that's not working, and the assumption is that this is based on a lack of resource usage or utilization, which is often phrased in different terms, like quality of service is bad, it's not snappy, time from start to end of some arbitrary operation is just too long. Yeah, these are things that you hear, and profiling tries to measure the time that is spent in scopes. Like scopes here are scopes in a programming sense. Like in Rust, you have a curly bracket that opens and a curly bracket that closes, and that's the definition of the scope. And what profiling does, it really gives you how much time was spent in this scope compared to the total program execution. Now, for profiling tools, sometimes they're also called tracing tools. You have a pretty large pool of choices. You have the traditional flame graph, like this is the flame graph plugin for Cargo. A newer execution sequencer, Puffin. The pretty popular tracing library, which is created by the Tokyo project, but doesn't really depend on the project, and it works entirely by adding instrumentation tags to your functions. No matter if async or, well, it matters a little bit, but not really that much. And there's also tooling for bigger scale, like Jaeger. It comes from the Java world originally, but it really is a transaction-based sequencing tool. So what Jaeger does is it collects all your data, but it has kind of a primary identifier, which is kind of a transaction key. And based on that, you can follow individual transactions throughout your whole system. So you don't have the clutter of having a ton of messages, which all do the same thing, but are kind of overlaying and create a lot of like visual clutter and lots of logs, but it kind of allows you to pick out one individual like causality chain that went wrong. So within your program execution, it essentially shows you one path and which part took how long. And that might actually be really helpful. Like for the remaining part of this talk, I'm going to show a couple of demos. And I created a small demo application, which essentially uses the image crate, decodes an image, then splits up into 2 threads. In each of them does a grayscale decoding. Like it's intentional that this is duplicated code. And then does edge detection for the Y direction, for the X direction, and recombines that to calculate the total edge amplitude. I marked the edge Y component here as red or reddish, because that's the part that's going to be modified to show some properties of how profiling reacts to that or not. So let's start with FlameGraph. FlameGraph is, at least on Linux, based on the perf tooling and creates an SVG out of that. I'll show you an example real quick. Yes. Here we go. This is the flame graph. It's just a plain SVG file, as you can see. And well, with Firefox or Chrome or whatever browser you're using, you can see which scopes take how much time based on the total program execution. So if you scroll over that, it tells you this operation takes 36.91% of your total execution time, which is the image operation of filtering a 3x3 filter over the image, which is the Sobel operation, which I showed you before, and which we're doing on the grayscale image. Now, this is not really surprising that we spend most of our time doing that, but it's kind of hard to tell, like we're doing that operation on each thread, like both for the X and the Y direction. The first step is to convert to a grayscale and then filter 3x3. In this case, we don't see like which thread executes that. It just shows us within this scope we spend this much time, which is not really helpful because we could spend 90% in the Y direction and 5% in the X direction and 5% in another unknown area, which is maybe implicit. So the question is, how does that help us? Our application is multi-threaded. It doesn't really show us multi-threading in the flame graph. Yeah, so it's kind of hard to take any conclusions from that. But that kind of poses more the question, like, what's actually our goal? What's the question we are asking? And is it the right question? Usually, it's not the question, what is slow, but what's the path to making it fast? And fast in this case means we want to optimize throughput or latency, or maybe both. But we can't optimize both at the same time. That sometimes is possible, not always, but that is our constraint. But we want to optimize the end-to-end execution, either regarding throughput or latency. And usually nowadays everything is heavily threaded, so it's not like 20 years ago or sometimes in embedded where you have one thread that just runs and consumes input and is one giant state machine. So everything is essentially linear. Another big thing here is the influence of locking. Like, how does making one part faster influence the locking sequence of our entire program? And that's really hard to tell. That's hard to reason about. It's also hard to reason about like which component or scope we need to optimize versus our entire system to make our entire system fast. And that's where causality-based profiling comes in. Well, with the emphasis on causality, obviously, and that's cause. It's, as far as I know, the only tool that's available right now that does this. And it's a little bit like all the other tracing tools. It's a little bit like Mick Jagger, which, yeah, where you have to do annotations in source code. So for cause, you have to add scopes or begin and end tags to annotate for throughput measurements and progress tags for latency. But really, scope and begin and end are just like progress tags with a special notation, which cause is aware of. So now with cause, you can plot your graphs like this. On the left-hand side, you see a couple of points I defined. I'll show you quickly. In the source code. So this is our decode from our last step. This is our encoding WebP file. We use one demo image. This is a little bit of state keeping of recombining the X and the Y image back together. It's a very primitive approach, so don't use this. And yeah, then our main function. And there we see the cause thread init, and we see the individual threads that are spawned. You see the rethread, which essentially just decodes the image from raw. We spawn another thread, which does the Y edge calculation. It spawns another thread, which does the X solver operation. And last but not least, we do a recombination with the custom implementation I've just showed you above, the pair. It's called pair and combine. So in each of those threads, we have a cause thread init. I'll come back to that later. A couple of, like a cause scope. So it measures how long it uses that scope for the performance experiments. And the progress tag, and another progress tag. And all of these are interconnected with channels. So here you see edge X, and in our graph that we've just seen, we have a edge X. Now we can remove all the other ones, and we see a graph that shows us the influence of speeding up that particular section and the total program speed up. Like, it's a little bit cut off here, but that's the total program speed up. So we see that if we increase this particular line by 80%, then the program execution time is sped up by 50%, which is fair. That's a nice improvement. Now, this is like one thing. You can also see that edge Y doesn't really do much. It has kind of the opposite effect. But you also need to account for the scatter here. And it's really scattered all over the place, so take it with a little bit of caution. But it gives you an idea of what to do or not to do regarding your total program speed up. Now, this was for the symmetric case, where we have grayscale and filter on both paths. Now, if we remove the majority of time spent of one path, so we comment this out, I would theoretically rerun this right now, and we would all wait and watch this for 10 minutes. And then we would see a different graph. I'll quickly show you that too. So now we see a mess of graphs, but if you get rid of most of them, edge X and edge Y are now it's a little bit more helpful. We see that the speed up on the XPath is all of a sudden like significant. Like even small increases improve our total execution time of our program significantly. Remember, this is for one particular file. For one particular line, just increases by 10%, we would get a 160% speed up. Unfortunately, this doesn't really like work too well with the sources in Cargo Registry. But if you have bigger projects, you can limit your scope to what is actually within your project, and then you can see, like similar to these graphs, you can see hints and pointers to what is worthwhile touching and improving for the overall execution time. So, and there are quite a few actually. Like not all might seem to be necessarily worth investigating. For example, these ones here are clearly not very helpful or conclusive. Like you see, like the spline interpolation sometimes is misleading because the data points actually just squiggle around the 0 line. So probably not a good candidate to invest your time in. On the other hand side, also the negative ones, where the slope is red, and that's a hint for congestion. That means you have a lock that is preventing your program from continuing. So it's not only like the rising edge shows you what's worth to improve, but it also shows you the falling edge where an issue is, like in which area to look for issues with locking. You can also see that the conclusion point, like the last stage, really has no effect. Like it's on the common path. So we can quickly go back to the source code. The conclude was here in the case where the X and the Y image are both available, and we can recombine them. And at this point, we enter the scope conclude, and we're done. And this is like on the common path. So as expected, there's no gain to be made. Like no matter what we do, speedups are really just noise essentially. We can look at a few more here. The reading is similar. Like read is unfortunately also blue. Like it's just like it's in the common path, so it doesn't really matter. And that's what I wanted to show you. And here, if you want to run it yourself, then what you have to do is go into your project directory. Just a normal Cargo project. What you need to have is you need the profile release debug, because for profiling to get accurate line information, you need the dwarf debug information as part of the binary, but you want to profile your release build, so that's why you add the true here. And then I never can remember the invocation. What you do is cause run -- your target, cause demo is our binary, and we just run. So in this case, it picks up all the Rust source files. That's why we also got the long paths in the overview, and then it starts the profiler thread. I'm gonna come back to that later. And it essentially just runs the binary and does performance experiments. I'm also going to explain that in a second. But we can also limit the number of files it's going to look for optimization potential. So we can just say, okay, please just take whatever is on the source, because nothing else is important to us. And then it becomes this. Unfortunately, our binary here is so small that it doesn't really yield anything. Like there's no optimization potential in here. It's a single file, so there's not really much for cause to split this up into. So yeah. So how does this work? This looks a little bit like black magic, right? We put some tags in there, and all of a sudden we see the influence of how much time an improvement on line X does on the overall program execution. And it's not really trivial how they do it. Because essentially what they do is they don't just measure what's executed, but they actively modify the execution. So every once in a while, they inject a delay in all threads, but one thread, except for one thread, and that's the thread with the cause annotation, with the cause progress, or the cause begin, end, or the cause scope macro invocations. So that means in relation to the other threads, you get a virtual speed up by that. So the thread we are currently on, which is tagged with cause scope, is sped up compared to all the other threads. So the delay injection here is the most complex part, and I'm gonna say a few more words to that. But the injected delay is actually randomized. So it's a little bit like fuzzing, a very light version of fuzzing, combined with tracing. So you tracing in the sense of measuring time. The way that this works is not very, but it's very sophisticated. What they do is they preload a binary which tracks a couple of counters by injecting itself into all POSIX calls. So every mutex lock, every mutex unlock, every condition variable, each of them accounts for a counter for the time that was spent as part of the delay budget that was needed for that particular experiment. So that's really, really complicated, like complicated mechanic, because you need to have certain compensation mechanics from condition variables that take longer than anticipated, and a lot of very small, nitty-gritty details, which they seem to get right. But I would like to defer you to their paper and their YouTube talk, where they detail out the mechanics in a lot more detail than I can do right now. The paper is very approachable, so it's a 13 pages paper. I really recommend you to read it. It's very interesting. Now, we've seen that we can get fancy graphs by line to total system time. Unfortunately, that requires that the whole execution is easily repeatable. And you also need representative input data in order to get representative graphs. If you feed for example, the image decoding and encoding parts, just plain white pictures, that might not yield you very good statistical evidence of what is worth optimizing. Because if you have images with color profiles, you need color mapping. So that would not show up if your input data distribution is not representative of what your live data actually looks like. So yeah, the best thing is if you have a horizontally scaled system where you have multiple nodes and run the same service on multiple nodes, just pick one node and run cause as part of your deployment and collect the data of a real world system over a couple of hours, couple of days. Yeah, because you can actually adjust the rate of the experiments as needed. So it's not like every millisecond a new experiment is executed. You can like tune that down, and that's actually really helpful. But it also comes with a few pitfalls. Like for a flame graph, you usually need a couple of seconds, like one run of your application and you're done. You have sufficient data to create the flame graph, and that's it. For the simple application I just showed you, it takes roughly 5 to 15 minutes to get sufficient data to see graphs that allow you to draw conclusions. With 1 or 2 data points, it might be just noise. During my experimentation time, I coded that up pretty quickly, so I used unbounded channels. And obviously, reading and decoding an image from memory is way faster than doing the Sobel operation on 2 images in parallel on your CPU. So the channels grew unboundedly, which meant that it was eventually cutting into swap, and I was really confused by why the graphs did not make any sense at all. So that's something to keep in mind. If your system is having some other anomalies, that might skew up your performance experiments and thus screw up your graphs. So that's something to keep in mind. And the Bezier interpolation of the plot representation is sometimes misleading because it's a Bezier curve. It's a mathematical representation. It has extremes which might not necessarily be there. So that's something to improve upon. Another thing is that you right now need an online service to plot all of those graphs. Like there is no command line utility or thing that you can run on your own PC as far as I remember. So you need to upload your traces, your cause profile there, and get the graphs there. The format is pretty simplistic, so it should be fairly easy to derive a parser from that. Yeah, any questions? Question, are these annotations compiled away on release compile? No, they're not, and that's intentional. These are necessary because at that point, cause knows that this is an entry point where performance should be sampled. Like that's the entry point at which all the other threads must be slowed down if a performance experiment is run for this particular thread now, or this particular scope, to be precise. So it's intentional that they stay there during release builds. So what you commonly do is you make the cause command line flag, like you add a feature to enable cause explicitly. Or what I've just figured out today is that with the Tokio tracing, there's actually a backend for cause. So you can just use instrumentation and use a different collector and use cause with that one. So that works as well. And yeah. Another question, how does it avoid the slowdown masking some natural latency, for example, waiting on cache or disk? It doesn't. It takes your system as is and optimizes your program for that particular environment. So it doesn't say, like, if you had a machine with more threads, that would be awesome, because then it would be this much faster. It just tells you for the particular machine with the particular amount of OS primitives, like the speed of your file reads, the speed of your OS primitive implementations, the speed, like the number of threads you use for certain operations, no matter if you had more to spare or not. It just tells you for this current setup, experimentation-wise, it would make sense to adjust this line to get this increased output, speed or throughput, latency. Christian, I'm not sure what you mean by that. But Tokio Tracing has an open telemetry backend, and there is a adapter for Jaeger to open telemetry. So I'm not 100% sure. I personally only use Jaeger as a standalone thing, like in parallel to Tokio Tracing. Another question, how big is the performance penalty introduced by cause itself? So cause works by using a signal to collect the performance counters. Well, it's counters exactly for that reason, to be lightweight. And it takes these counters and collects them over a couple of milliseconds. And if I remember correctly, every 10 milliseconds, it does an evaluation. The evaluation is based on the program counter and a couple of other things. I don't remember exactly. And that's all pretty fast. It's all integer operations, and it's not that many of them. Yeah, like in practice, I don't think it's very measurable. A very good question. I actually didn't measure it. Just a gut feeling. Gut feeling from manual execution and hyperfine statistics. Any more questions? Question, so if you don't run cause, introduce code by the macros don't impact the runtime at all. I think it doesn't impact it at all, because all the logic is part of the LD preload. So if you skip that LD preload, nothing is really executed in that sense, except for a couple of counters. Not a couple of counters. Like the cause, call, and scope is still there. But other than that, there's no logic executed. So it's really bound to that LD preload. If you do that, then all of your POSIX calls get one level of indirection, and also every 10 milliseconds, one of those calls will eventually do the evaluation. Yes. Question is, so it's all right to leave all that stuff in on final release. The idea is that you actually have it always in the release, and if needed, you can do performance experiments. Like if you encounter bottlenecks on all of a sudden, then it's just an easy LD preload and you're good to go. I'm gonna go back a few slides. Here. So yeah, I really recommend to watch that YouTube video. They do a pretty good job at explaining the mechanics, and also the paper. Oh yeah, and I wanted to say one more thing about the init thread. Forgot about that. There is the init thread. This init thread is needed because the evaluation logic is run in a signal handler. Now, the default signal handler stack size of Rust for signals is not large enough to allow the calculations that cause needs to derive all the counters. So we need one per thread there. Like each and every thread that we spawn and that we want to, each and every thread has to have that. Otherwise, any performance experiment within that thread will cause a stack overflow, so a segmentation fault, and crash your program. Cool. Thanks for joining. I'll be around for a bit in the Discord channel. So if you have any further questions or want to discuss anything, then I'd be very happy to chat to you there. All right. Have a good night. And it's very most likely gonna be the last one. The last Rust meetup for this year. So I wish you a Merry Christmas and a Happy New Year, or Happy Holidays. And have a good one. Enjoy your time. Enjoy your downtime. Code some Rust. Have a good one. Bye.